Good morning, fellow programmers. Thanks for joining me. I'm T-Pain, and welcome to Let's Learn C++. Feel free to use the skip ahead feature on the right-hand side to jump to any specific sections or examples. Make sure to have annotations turned on so you can see the updates I make to these videos. Today I'll be using Visual Studio Community Edition, which you can download from visualstudio.com. However, you can follow along with whatever you like. Today's focus will be on functions part 3, constants, recursion, overloading, and various other stuff, which built heavily on previous lessons, so check out those if you're unfamiliar with a topic. If this is your first programming language, I'd strongly recommend checking out my Let's Learn Python series, which teaches you the fundamentals of programming. All you need are the Basics and Object-Oriented Programming series linked to the right, and you'll be well prepared for this C++ series. Alright, so let's begin by talking about const. Const is short for Constitution, which no longer holds any weight in the US of A, now that Trump has been elected a few days ago in the presidency. It's a terrible joke, but really relevant at this point in time. Hopefully someday this is a totally obscure reference that nobody gets. Alright, so everybody knows my political stance now. Const is a keyword that is used to declare a variable as unchanging or constant. I want to emphasize that const is short for constant. The keyword may be placed before whatever is being declared as a constant. So let's go ahead and copy and paste some code. The very first line right here, line 5, we have const int I is equal to 5. And that's as simple as it gets for declaring a constant integer or a constant variable. You just place the word before the variable name or the variable's valid identifier. For those hardcore programmers out there. If we want to declare a regular variable, it's just like that without const. Now, right here, line 7, I want you to note that I put I equal to 4. And this results in an error, a compiler error. You'll notice that little red underline under the I. That's because you cannot change the value of a constant. Unless you want to go into the crazy roundabout way of changing that and like const casting, but we're not going to do that. Instead, just know generally you can't change that variable's value after it's been set with const. However, one of the benefits of that is that we can, since the variable is constant, to declare that size of the array. We cannot do that with regular variables, however. So if we have array2 and we set it equal to j, we get a compiler error here too. It's saying it must have some constant value. And ordinarily we would plug in a number right here and just put 5 or 3 or something in here, and that would satisfy the constant value. But variables won't actually work for that unless they are constant. Cool. The way to get around that, however, if you do want to create an array with a variable size and it's not constant, is to actually do a dynamic array where you create a pointer to array and then set it new int and then the size of the array right here with j. And notice that j is not constant and it works just fine. If we did substitute I, that would also work. So constant or unconstant variables work fine when you're using a dynamic array right here. We'll get more into dynamic allocation of memory in the first intermediate tutorial after this basic series. So don't worry about it if it's confusing at all right now. Now here I want to show you that you can actually change the placement of const, and it has different meanings based on where it is. So both A and B say the exact same thing, which is that they are going to be holding an unchanging variable value once it is set. Now in the next line we have placed const after the star or asterisk to designate that this is a pointer, but before the identifier of C or the variable's name of C. And this is saying that we're going to be pointing to an address that never changes. The address is never going to change for this pointer, but the value inside the address could change. So it basically is a pointer to a permanent spot in memory, regardless of what happens to that memory. And here we just set it with a new int and then setting the value to 4. Finally, I want to show you the last place that you can place the keyword const, and this would be in a class definition. So if you were inside of a class and defining a function, you'd place const afterwards to say that you were never actually going to change the member values of the class, or you're never going to change the data values within the class itself through this function. Everything would remain constant. And so const allows the compiler to do stuff a little bit more efficiently. I want to note that const vars can be made from non-const variables. And then you can do this by typing const int and then your new variable name x and passing in parentheses your old variable of y. You're like, all right, Sharvid, this is great and all, but what does const have to do with functions? Besides this weird class implementation that we're not going to use for a while. I bring this keyword up now because at times when creating a function, it may be unclear what parameters are going to be altered or changed within a function. Const solves this issue by explicitly stating a parameter or variable as being unchanging. So let's go ahead and examine some new code. All right, so I've copied and pasted some code here, and I've collapsed these two functions so we can just focus on this first one. So it's just a simple function that doesn't return anything, and it's called add ham underscore ref. So what we're doing is we're passing a string by reference so that we're not actually making a copy in the string, we're actually grabbing the raw data. And here we're just adding ham to the end of it. So we're adding ham. That's the name of the function. Makes sense. And then we're going to go ahead and see out of it. And here, everything compiles just fine. Now, what happens when I add const before it? Now it no longer compiles correctly. We get a compiler error here saying we can't actually manipulate the const variable or the string variable. Now it's giving us an error. That's exactly what we would expect with the const keyword being in front of the variable type. We're saying that we're not going to change this ever. And this is also true for not just references, but also if we're passing in a copy. So notice we do not have the reference operator here or the ampersand symbol here. Instead, this is a copy, and it still does not compile correctly. And so the const keyword stops us from being able to manipulate it in any way. Cool. And that also holds true for pointers. If we place this keyword before the data type and before the star, then it will actually stop us from trying to manipulate that string copy. Very cool. So now we've got a clear way to indicate that we are or are not going to be changing parameters passed into a function. Cool. So the const keyword is a way of saying that this is an in-only variable or parameter that we are not going to be changing at all, and it's just being passed in. No changes are going to be made out to that memory. C++ core guidelines F.16 has this to say. In-only parameters copy simple int and char parameters. Meanwhile, const references can be used for more complex parameters. This is to say that if the parameter being passed in is small in byte size, like an int or char, just pass it in as a copy without const or directly referencing the data. If it is large in size, like a string, item collection, or custom class, pass it in by a const reference. F.17 says in-out parameter references should not be const. So if you are, again, manipulating the data in any way and changing its value, then just take out the const. Cool. And now I'd like to talk about compile time versus runtime. So compile time is when you're compiling and building the program to run. Runtime is when it actually runs and executes line by line. Now runtime, when the program's actually running, is typically where you're going to be placing const, the keyword that we just learned. Instances where you'd see this is when you define a function like f, and you have one of the parameters as being constant, so you just use const int I. Or another instance that you'd use const is if you're getting a user input through cin or something and then casting it as const and then converting it to a const. Const expression is very, very similar to const as in and of itself. In fact, most of the time that you use const, the program will work just fine. But there's very few times that you want a constant to instead be a const expression or const expr. So for instance, we've learned that we could create a constant variable through const int I is equal to 6. This would actually be an appropriate place where you could substitute in const expr instead. Now, I personally haven't come across too many instances where I absolutely needed a const expression, but it is a tool for your toolkit nonetheless. So if you're simply stating constant variables and defining their value right then and there, const expression could be good. But if you're converting it from an unknown variable at the time, then it would be appropriate to use const. It smells like cat poop in here. Purple. Now I'd like to talk about the keyword inline. Inline is a keyword that we would place before a function that is used to replace any instances where the function is called with the code itself. It is used to increase the execution time of the program. The keyword inline is ignored, however, if the function is too long. The purpose of this is to save the overhead of function calling and returning, but it increases the code size to be even bigger and requires recompiling every time the code is changed. So let's go through an example of this. So to start off, I am just including the IO stream to output. I am including a string, and I'm also including something from the boost library. And I just wanted to include the timer.hpp file. And also that HPP is just an H file or a header file, but the PP stands for C++, so it's a header ++ file. In case you were curious, nerd stuff. So I'm going to go ahead and close out that window, and let's examine the code. We're using namespace standards as well, and then right here is our first inline function. And it's just inline placed before the return data type right here of string and the name of the function, which is add ham inline. And it's just going ahead and adding the word ham to the passed in string, and that's it. The string below that's called add ham reg is just with missing that keyword of inline before string. So it's the regular version versus the inline version. And what we're going to do is we're going to test these two out to see which runs faster. All right, and now below here, we have an instance of our timer right here. Then we create a string called A, called testing, and then we output the elapsed time. So this is our start time. Then we're creating a simple loop that calls the add ham inline function about 100,000 times. Okay, then we're going to print out the elapsed time, and then we're going to repeat this, but for the reg version. Now, I added commented versions of the opposites right here, and I'll show you why in just a second. Then finally, we print out the timers, the time elapsed between the two, and end it. So let's go ahead and run it and see what's going on. So here we can see it outputting the results. The first is it takes, for 100,000 iterations of the inline function, it takes 1.164 seconds. The second one takes 2.45. So this is roughly about 1.1 seconds to run the inline version and then 1.3 seconds to run the second regular version. So it's fractions of a second, but 0.2 is the difference between the two. So you may be thinking to yourself, well, it's probably because there's like some sort of compiling or something in the background. Maybe it's not as fast if we do it in the reverse order. So let's test that theory. And now we're going to delete these comment lines right here, add them to the line below, repeat this for the next one, save it, and now we're doing this reverse order to see if they do perform differently. And indeed, they do perform differently. Now notice that this takes about the same time as the last one of 1.1, and the inline version takes, again, about 1.1. So now they're at about a tied pace, where they're doing about the same time. So the inline is performing when it's placed second about as fast as the regular version. So very interesting. When it's in reverse order, the inline far surpassed the regular version, but when it's reversed, so they have the regular version first, it seems to go at about the same speed. So take it with a grain of salt, but know that it's something that you can use to optimize very simple code. If you typically have like 1 or 2 lines of code right here, then you can use inline. Alternate solutions are also Lambda functions, which we will cover in a later intermediate tutorial. All right, so let's move on to preconditions and postconditions. This next section builds on the GSL library we installed in tutorial number 8 under additional library installation. We're going to be focusing on the function calls of expects and ensures. If you're developing your own functions, you may want to make sure that other programmers are passing in valid arguments. 2 functions included in GSL do just that. Expects tests for preconditions and ensure tests for postconditions. So for example, when you go to a party, you are expected to dress nice. When you leave the party, you ensure that you have your keys. They both function exactly the same, and the program doesn't really care where they are. It's more for clarity and the programmer's benefit. All right, so let's go ahead and look at a simple example of this. All right, so what's going on in this function? First, we import our GSL, and I'm just importing the header file to get the ensure and expects functions. Actually, they may be macros, I'm not really sure. But what we're doing in this first function is we're going to check the square root, or grab the square root of this, and I didn't actually implement the square root function. I just wanted to illustrate that this is how you'd use the expects function. You would expect that anything passed into a square root function would be at least 0 or greater, so that if it is negative, it won't return some imaginary numbers or crash our program. The next function is called area, and it's just taking in the width and height, multiplying them together, and then finally we have an ensures to ensure that the area is itself positive. If it is negative, that means the width or height were negative. Okay, and then we're just returning that value. Now let's go ahead and test out this code. So we're going to go ahead and call square root function and pass in a -2 to see what happens with that square root error. Okay, and now notice what happens. Our output box doesn't output anything at all, but we have a pop-up error that says there was a breakpoint that was triggered. And then the wonderful thing about this is that there is a tiny arrow over here that is pointing to the exact line of code where something is breaking. And then we can click this button, break, and it stops our program right where it's at. And now if we mouse over it, we can see at X, it is a value of -2. Basically the way this works is what you do is you pass in a Boolean check for some value. And so that's us just checking the value of X against 0. You could pass in whatever condition you want to check against though. Cool. So that's how expects work. Let's go ahead and call area. Right below it, area. And we're just going to call -1 and 1. All right. And then we're going to comment out the previous line of code, run it, and let's see what that does. Again, it causes a triggered breakpoint. We're going to go ahead and break the program. And again, the arrow is pointing us right to this. This is extraordinarily useful. Now, you may be asking yourself, why don't we just use assert? I mean, assert would work just as well. I mean, that's the C++ way of throwing an error to the programmer. Well, let me show you what actually happens. So instead of assures, I'm just going to go ahead and replace all this code with assert. Okay? So instead of expects, we're now replacing it with assert, which is testing in a very similar way, but acts dramatically different and less useful. You'll see here in a second. Okay, so we get this output pop-up that says assert failed, and then it outputs the line and it outputs the file. Now, how is this different? All right, so we're going to go ahead and break it, and look at this pop-up box right here. It says no symbols loaded, shows you a whole bunch of garbage stuff that you don't really care about. You go back to the regular code and there is no arrow pointing to our line of code. Instead, we're looking at this output box to debug our code. We have to go in and be like, okay, so it's this file, yeah, and then we're gonna, let's see, line 8, this is, okay, there's the assert, okay, now I found it. Versus the expects and ensures act so much simpler. All right, now I'm going to delete some of this code and separate this out into header files so you can see even clearer how this is awesome. All right, so what I've done is I've split up the code between 3 different things, and you can write these out real quick. We have 3 different files. We have a square root header file, we have a square root CPP file, and the main.cpp file. In the square root header file, we're just saying if and def, the square root, define that square root, and then we're just creating a prototype of that function and then ending that function. Then in the actual C++ file, we're going ahead and we're importing the GSL, which we're going to be using. We're going to import the square root file and then defining the square root function just as before with the expects of x is greater than 0. So we've simply migrated around everything we had before. And then finally here, we are only importing the square root header file, not the GSL. And now watch very carefully what happens now. I'm in the main CPP file, all right? I'm gonna go ahead and close out the other 2 tabs right here. So we only have the main CPP file. Watch what happens when we run this debugger mode now. All right, now we get a pop-up of black just as before. We get this triggered breakpoint right here. And then just as before, but notice what happened. It actually opened up the file that had the breakpoint triggered right here at line 5 of square root.cpp. So it opened up the file for us. It led us right to the line for us. And so all we got to do is hit break. We can mouse over and see exactly where the error happened, or exactly why it happened. So notice how much time that saved. You saved seconds, precious seconds. But imagine doing that every day for long periods of time. Like at some point, you may deal with dozens or hundreds of files possibly, and navigating through all of those to try to find that one weird file where that bug happened could be cumbersome. Instead, this is awesome for saving you time and energy. We're programmers. We're technically lazy. We want to find the most efficient way to troubleshoot our problems. And this does just that. So this may not seem like much, but this is super powerful and will save you a lot of time down the road. All right. I will stop preaching the good word about expects and ensures. All right. The C++ core guidelines interface section, specifically I.5, I.6, I.7, and I.8 recommend this technique. All right, so next let's talk about recursion. All right, so if you recall from our Python series, recursion is the act of a function calling itself from within itself. And here is a simple example of a recursive function called factorial. And factorial, if you recall from math, is represented by 5 exclamation point. And it means to do 5 times 4 times 3 times 2 times 1. So you're multiplying from any high integer downward, counting downward against every previous number. You can't see it, but I just made a hand gesture moving downward while I was talking. So the way factorial works is we're going to be returning a long int. We haven't been using long very many times, so I want to throw it here. And then we're passing in a long int here. We have the call to the good old GSL expects, because I want to start using this whenever it makes sense. And we expect that the number passed in, I, is going to be greater than 0. If it's 0 or negative numbers, then it's going to cause problems. So we'll simply throw an error if it is. Then we have a check to see if I is less than or equal to 1. Then we're just going to return 1. If it's not, then what we're going to do is call that function itself at one less version of I and multiply it by I. So essentially, this will result in 5 times 4 times 3 times 2 times 1. Once it hits that 1, then it'll actually resolve, and it'll chain back up of doing all that multiplication and be resolved. So if we do factorial 3, it should result in 6. And I forgot to set a breakpoint. There we go. Save, set breakpoint, and there we go. We get 6 being output. Awesome. And that is it for recursion. Now let's talk about overloading functions. Overloaded functions are functions with the exact same name, but with different parameters. Now let's look at a simple example of overloaded functions. We're creating a function called add here, and it just takes int a and int b, and then we're returning int a plus b. That's it. Here we're creating a second version of that add function, but what's different is that it actually has parameter c being passed in, and we're just returning that. So now we can create below a call to that just by saying add and then 1 plus 2, or 1 and 2 being passed in, and it would work just fine. I think the program's getting angry because I'm not actually including the proper main function at all. Okay, so now it's happy. But basically we can now call add with 1, 2, and if we wanted to, we could call it with a third parameter right here, and it would still work just fine. So now we can do it with 2 or 3 options, and it'll still work. Now, this third method is actually the preferred method to do. Overloading functions by doing these first 2 functions that are like pretty identical, but the third parameter is being added on, is inefficient. It results in like much more code. So what if we had like 4 or 5 more variables being added in that we want to throw in? Like we want to have just a lot of options for the player. That would result in this code being duplicated many different times. But instead, what we could do is use default arguments instead, and it'll cut down the amount of code that we have to do significantly. So we could actually, in place of these 2 different functions, replace it with this third function that just has the default value of c equal to 0. We could also throw in an int d equal to 0 if we wanted as well, if we wanted to check for a 4th parameter. And now we could just do plus 3, plus 4, and it all works just fine. Any version of those. C++ core guidelines F.51 says prefer default arguments to overloading. And I completely agree with this. This will reduce the amount of code that you have to write, and less errors will be made. Just prefer default arguments with the equal to versus having a bunch of different overloaded functions, unless you really can't get around it. If you can't get around it and you have to create all the different versions, for instance, maybe you want to have a version with float or doubles, then sure, do it. Finally, I want to leave off with a note. We will be discussing shared pointers, unique pointers, lambda functions, dynamic memory allocations with new and delete in a much later intermediate tutorial. Thanks so much for watching. Great job keeping up. Definitely try these coding challenges shown here and the debug challenges linked below in the description. Please leave me a comment below if this helped you at all, and also check out the comments if you're having problems. Please share this tutorial series with someone special and maybe support me on Patreon. Thanks so much for your support, and as always, like, subscribe, and keep the dream alive.